We're here at our 25th convention, and this one's in Arizona. And I guess this is the first time we've heard from your company at our conference. Heard from Musk a number of times and from some other people over the years, but this is the first we've heard from you. Now, your company, though, of all the so-called new space companies, is really only two that have created an operational launch capability, SpaceX and Rocket Lab. And so far, as I understand it, you only have a small launcher, but you have a medium lift launcher that is getting ready to go on its first flight. But anyway, let's start at the beginning. Unlike Musk or Bezos, you were a working engineer and you managed to get investment to create your company. That is, you didn't use it with a few of your $100 billion.
Yeah, the old-fashioned way.
Yeah. So tell us about the origin of Rocket Lab.
Yeah, so I mean, look, I started the company down in New Zealand in 2006, and we launched a first sounding rocket in 2009. And then I went to Silicon Valley in 2013, and that's where we raised the first capital for the Electron program, a small orbital class vehicle, and became a US company at that point in time. And yeah, I guess our journey was quite a lot different. We raised venture capital and funded the program that way. And then ultimately, listed on the Nasdaq last year. So we often joke that this is a non-billionaire funded space company for sure.
Right. Well, you've outperformed several billionaire funded space programs.
That's very kind.
Okay. So the first you did the sounding rocket, and then your first orbital launch rocket was called the Electron.
Correct.
So tell us about the Electron.
Yeah, so the way to think about Electron is our friends over at SpaceX took what used to be a $300 million launch and brought it down to $60, $90 million, depending on the mission. We kind of did the same for small launch. So if you had a small dedicated payload that you had to get to a particular orbit on a particular time frame, you had a Minotaur or Pegasus or something like that, and it was sort of $50 million price tag. And we took it down to sort of $7.5 million or thereabouts, for Electron. So, we like to say that SpaceX disrupted the large launch scale market, and we did the same down in the small launch. And as you point out, we're now kind of also looking to move into the medium and large launch. And apply all the lessons we've learned from operating a launch vehicle in a company to that vehicle to create even more capabilities and more options for folks.
All right, but Electron. Okay, so I know a little bit about it, but would like to. People here probably would like to know some stuff. There's about 150 kilograms to orbit. And you've used it to launch a large number of very small satellites.
Yeah, so we can actually lift 320 kgs to a low Earth orbit.
Oh, really?
Yeah, yep. And we've got number 32 sitting on the pad right now. So it's actually the second most frequently launched US rocket behind our friends at SpaceX. So we launch a bunch. We're pretty much on a monthly cadence. This year we were able to demonstrate 2 launches 15 days apart. Every 20 days or less, there's a rocket roll off the production line in the factory, it's become the workhorse of that small launch, dedicated market.
Of like 6U CubeSats, this sort of stuff.
No, we don't really. We fly very few CubeSats. Generally, they're sort of 100 or 200 kg, dedicated spacecraft. Ranging from missions for the NRO through to smaller missions, of course. But we put some 150 satellites in orbit now. But generally, I would say the majority of our customers are sort of in that 100 to 200 kg class of microsatellite or small satellite.
Right.
Very capable machines in doing important science. The one we just launched a week or so ago was General Atomics Argos satellite, which is obviously for wildlife monitoring. Generally 1 or 2 satellites on board each mission.
Right. Now, you've followed the SpaceX model of developing your own engines as opposed to trying to buy them from vendors at significant markup. And so you had, the Rutherford engine in the Electron? And as I understand it, unlike most liquid-fueled engines, you didn't use combustion to drive the pumps, you used electric motors?
Yeah, that's correct. I mean, we've very vertically integrated across the whole, the whole supply chain. And it's literally raw materials in one door and rocket out the other. We 3D print all of our rocket engines. We've put, over 300 rocket engines into space now. And as you say, we chose a different cycle, not to try and innovate for the sake of innovating, but on a small launch vehicle, propellant margins or propellant residuals are everything. So if you leave 20 kgs behind in a propellant residual in an upper stage, and you only carry 300 kgs of payload, that's a significant deficit in your payload. So the really hard thing about small launch vehicles are actually managing propellant residuals, and the electric pump enables you to really effectively do that because you can continually change your oxygen fuel ratio and close that loop. And also you can consume all of your propellants because you don't need to worry about turbines overspinning or shutting down ox-rich or fuel-rich.
Does it also make the engine highly throttleable?
Very throttleable, yeah, incredibly throttleable, infinitely throttleable, in fact.
Right. So now the Electron is just an expendable launch vehicle, but if it's extremely throttleable, could it be made into a reusable launch vehicle?
Yeah, it is actually a reusable launch vehicle. Our approach is slightly different. We catch it midair with a helicopter, which I know sounds slightly unconventional, but we're we're in the final stages of that program. So we've bought 5 of them now from space. Generally, we splash them down. The last recovery mission, we actually did capture it with a helicopter. We subsequently let it go. But there's a mission coming up here pretty shortly that we'll announce where we will have another go. So it was really the learnings from the recoverability and reusability program from Electron that has enabled us to move so confidently into the Neutron, which is our larger launch vehicle program.
Let me ask you a different question, though, deviating a bit. The Electron engine, the Rutherford engine, what's the thrust? What are the propellants?
Yeah, it's LOX Kero and around about 5,000 to 6,000 pounds of thrust, so a pretty small engine in that respect.
Right. But if it's that small and if it's incredibly throttleable, have you thought about proposing it for use in a lunar lander?
Yeah, we've had many a folk come to us with that, for sure. The only challenge, of course, is it's an liquid oxygen engine, so you've got cryogens to deal with, as opposed to kind of storables. So there's an extra element. But yes, it has been considered for that. But the probably the more relevant thing in that respect is our upper stage photon satellite or kick stage. That is an on-orbit storable, really high performance stage that we delivered the capstone mission to the moon for NASA here a few months ago. And I guess one of the cool things about Electron and that coupling with the Photon spacecraft is that it enables like super low cost interplanetary and deep space missions. I mean, the capstone mission to the moon that we flew for NASA, our launch part of that involved launching of Electron, and then our Photon spacecraft spent 7 days in orbit doing these very, very delicate and fine orbit raising maneuvers to ultimately end up placing the NASA's capstone spacecraft on a TLI to the moon. And why that's kind of relevant and cool, especially in this kind of forum, is that that was a $10 million mission. So for $10 million, we sent we delivered a dedicated mission on a TLI to the moon, and that Photon spacecraft that we developed is is completely capable of going to Venus, going to Mars. In fact, I know this is strictly a Mars event, so I'll tread very cautiously about talking about Venus. But
nothing in the universe is foreign to us.
But we have a private mission to Venus here using that capability, where we will actually go and attempt to sample Venus's atmosphere. We're working with Sarah Sager and her team as a life finding mission. But we have that spacecraft has the capability to venture to these destinations for just an extraordinarily low price. And the mission to the moon for NASA was really exciting. But to me, what was more exciting is that we created a capability for space science to do frequent and affordable missions to Mars, to Venus, to their planets, near Earth planets, and asteroids.
So tell us a bit about that Venus mission.
Well, look, not playing favourites with planets, but I'm really very fascinated with Venus. I think it's an incredible analogy to Earth in many ways, and Mars has the attraction that you can put boots on the ground in Mars. Like we can put footprints on Mars and create sustaining civilization there in time. Venus, we're just not going to. There's going to be no footprints on Venus, which makes it a very, very difficult planet. And I think for that, one of the reasons why it hasn't been studied perhaps at the same level is because of that. But if we look at Venus's atmosphere, there is some regions in there that hold hope that there could be some markers of life. And I don't know, I got into, the youngest memory I have actually of my youngest space memory is standing outside with my father at the bottom of the South Island of New Zealand on a freezing cold night. And I don't know how old I was, but single digits. And him pointing out to me in the sky that all the stars in the sky were suns and the most probable planets around those suns, and there could be somebody looking back at me. And I always found that it's thoroughly unacceptable that we still haven't answered, from a scientific standpoint, you have to say that we are the only life in the universe because we haven't proven otherwise, right? So, although statistically I think it's pretty well accepted that there's the probability of life outside us is pretty high, but until you prove it, you can't stand behind that statement. So. I just felt that, we have a rocket, we have a spacecraft, we have an ability to actually go and search for life. And it would be pretty rude if you have all that capability to do that and you don't give it a crack. So, we have this private mission that's done in nights and weekends. It's got, philanthropic funding behind it, where we're going to try and just get to the atmosphere in Venus and with a nephelometer, and let's see if we can make some discoveries.
Right. Now, that mission is going to send a probe into Venus's atmosphere. It's going to come down with a parachute slow through the atmosphere, right?
No, there's no parachute. It's just a ballistic entry. We get about 210 seconds in the sweet zone. So it's a very, very simplified mission in that respect. Really?
Why didn't you use a balloon? You could have floated for weeks in Venus's atmosphere.
Well, yes, there's lots of engineering solutions that are far superior, but it's kind of what have we got, and what is the minimum viable product that we can deliver. I would love nothing more than a large program where we could send significant mass there and spend some time. But when you're doing it with spare qual parts and kind of philanthropic adventure, it's a high risk mission that I think it's important to try, but by no means is it optimized from both a scientific and engineering point of view. You've just cut out there, Robert.
Can you hear me now?
Yeah, I got you. Yep.
All right. So I actually do a certain amount of ballooning, and um, well, you could have very easily an extended duration balloon mission on Venus, and one of the more attractive ones uses solar balloons, basically hot air balloons with a vent valve at the top. You can go up,
Yep.
you can go down, you can do all sorts of things. Have a real good time. And perhaps after this mission, you'll think about a mission like that.
Well, I'm certainly hoping that after this mission, we inspire a whole bunch of missions back. Part of this is proving that it can be done, and it would be great if you found just enough science that made it tantalizingly interesting to cause plenty more missions to return.
Yeah. So let's talk about the Neutron. This rocket is in development right now. Tell the people here about it.
Yeah, so it's kind of based on the learnings of Electron, and it delivers 13 tons to orbit in a reusable manner, slightly less if we land it back at the launch range. It's a reusable first stage, expendable second stage, and we think it's going to be an incredibly important tool in the launch toolbox. It's got some unique functionality and features. I mean, if you look at it, it kind of looks a little bit funny. That's because
I think it looks great, actually. I think it looks a lot better than a Falcon 9. It's shaped more properly.
Well, I mean, so it's that shape because it's optimized to go up just as much as it's optimized to go down. And when you actually start with a clean sheet of paper to design a vehicle that is primarily designed to do that, then that's what you end up with. It's a very wide and large diameter first stage, and the primary reason for that is that one of the biggest challenges for reusability, of course, is re-entry, and reusability is a thermal problem, not necessarily a control problem. So the best way to deal with a thermal problem is not have a thermal problem. So if you have a very, very high drag area with a very, very low mass, then the stage decelerates, and the heating energy is significantly kind of reduced and controlled. So it makes and of course, if you don't have to deploy legs and you don't have mechanisms, and the wide base also helps you out for those particular things. So it's very much optimized for reusability. 70% of the cost of a rocket is in the first stage. So if you look at the difference in size between the first stage and the second stage, you can see that the first stage is optimized to do a lot of work. So we don't separate off the second stage until we're well and truly out of the soup, sort of 100 kilometers in altitude. And if you look at the second stage, it looks disproportionately small to the first stage. And the challenge with the second stage is it has competing requirements. It needs to be the most highest performance stage, but because it's not reusable, it also needs to be the lowest cost. So the more energy you can put into your first stage and get it back, the better off you are. So hence, the fairings on Neutron open up, and we kind of eject out the second stage in the payload, and then the fairings close again, and then we land. Because we want the first stage, to be as reusable as possible. We don't want to be gathering fairings up, downrange.
Right. So this is a methane oxygen vehicle, both stages.
Yep,
And what's the fairing size?
It's a 5.5 meter fairing, so with
5.5 meter.
Yeah,
okay.
The standard.
All right, and it's got this gaping mouth thing. There's a James Bond movie where someone has one of those in orbit that swallows up a capsule and brings them home.
It's funny. I'd never seen that until we released the video of how Neutron was going to work, and then I was inundated with that particular meme.
Yeah. Okay. Well, because it's perfect. And so 13 tons to orbit. It's quite competitive with. You're now going to be competing directly against Falcon 9.
Yeah. I mean, we think that's an interesting place to be, and I think there's clearly a lot of demand around that kind of mass. And it's a very useful mass for doing mega constellation work as well as interplanetary and as well as human spaceflight. So it's kind of that sweet spot where you get all the kind of elements in a vehicle size that's kind of optimized. It certainly can't do very large missions, but the cost you bear in building a vehicle that can do very large missions for the relatively small number of them, economically and both from an engineering stance, I think we believe we found the kind of the optimized point. History will prove us right or wrong, of course.
Well, it's certainly a very popular point for launch vehicles historically. And what do you anticipate the cost of a Neptune launch is going to be?
Well, I mean, look, the reality is that building a launch vehicle is an undertaking that results in significant grey hairs or loss of hair. So you wouldn't embark on it unless you felt that you could be competitive in the marketplace. Otherwise, it would be a completely pointless exercise. So one of the true advantages of building a small launch vehicle first is that there's so many elements of a launch vehicle that don't scale with the size of the launch vehicle. For example, like flight safety analysis and your flight safety team. It doesn't matter if you're flying a 20-ton vehicle or a 200 kg vehicle. The flight analysis and the flight safety analysis is the same. And that goes along with even manufacturing. Like if you're a technician on the shop floor assembling a 2-inch valve or a 12-inch valve, it takes the same amount of labour. There's a lot of things that don't actually scale. So by developing a small launch vehicle first and kind of going back to your initial point of doing it commercially, making sure the books have to close, then you're forced to really optimize and really think very, very hard about how you develop these systems and how you develop these teams. I mean, we can't afford to have a 100-person flight safety team. So we have to automate all of those functions and amortize, all of those overheads, if you will, into a rocket cost of $7.5 million. So we've become very, very good at automating things and very, very good at being highly efficient at doing all of the kind of the periphery stuff around a launch vehicle. And by the way, that periphery stuff is actually the majority of the cost.
Okay. Now, it's a methane oxygen engine. I think you call it Archimedes.
Correct.
And has maybe 120,000 pounds of thrust, something like that.
Yep.
Now, as you may know, I've been a champion of methane oxygen propulsion for a real long time. And it was the basis of my Mars Direct plan, because methane oxygen is the easiest propellant to make on Mars, and to use it for return. And one disagreement I've had with Musk about his version of that plan is that he's using starships to come back from Mars, which is very problematical to have to refuel an ascent vehicle that is so massive. Have you looked at all into the possibilities of altering the Neutron to be used as a Mars-Earth return vehicle?
To be perfectly honest, I have not. We're certainly making sure that it is human rateable. That is for sure. And we did not an announcement of a capsule. A few weeks ago, where we just kind of laid out, well, if we were to do a capsule, this is generally what it would look like. But I think there's a lot of missions that you could open up for sure with that kind of class and scale of vehicle. But I can't say I've thought of that one to date.
All right, not today. Well, it's a suggestion. Anyway,
I'll take it.
Okay. So one thing about the SpaceX is that they're developing a whole bunch of orbital capabilities of their own on orbit, that it's not just a delivery system, that they're doing the Starlink. In other words, they're creating orbital enterprises supported by their launch vehicles. Do you have plans along those lines or better lines? Yeah,
absolutely. In fact, our Space Systems division, which is the division that builds satellites and spacecraft, is bigger than our launch division. I think most people know us as the little rocket company, And perhaps, in hindsight, I should have called the company something different than Rocket Lab, because it tends to draw people's focus on the launch piece. But like I say, I mean, our space systems business, both by every metric, is larger than our launch business. And we're building some super cool spacecraft and involved in some really cool missions. So obviously we have the Escapade mission for NASA. The two spacecraft that are going to orbit Mars in 2024. We have commercial customers where we're doing re-entry of capsules for them. We have the Global Star contract, which is providing connectivity for mobile devices. I think we're definitely an end-to-end space company, and I've been very clear in my view that I think that the large space companies of the future are going to be end-to-end space companies, because when you have launch, you've basically got the keys to space. If you have a satellite division, then you can build the infrastructure. It's fairly logical step that once you can launch the infrastructure, build the infrastructure, that you would operate the infrastructure. So our approach is a little bit more kind of steady and methodical in that sense, and we're not pushing all the chips. We're certainly not pushing the chips of the company into the middle on one particular application. But right now we're very, very happy to supply and support everybody else's application. But we've made no secret in the future that we intend to provide a service of some sort.
Okay. Any thoughts about orbital research labs, space stations, things of this nature?
Everything's on the table. Everything's on the table. I like to finish one thing before I start the next. So right now our focus is on getting Neutron to the pad. And like I mentioned, we've got a lot of really complicated space systems missions to deliver. So, not one step at a time.
All right. So speaking of getting Neutron to the pad, when's that going to happen?
Yeah, we're trying to get something on the pad by 2024. And it sounds an ambitious goal, and look, truly it is. However, there's a whole lot of stuff that that are just directly come across from Electron. For example, like avionics are rocket scale agnostic. So we're at a huge advantage where we can take all of the avionics, flight computers, distribution nodes, everything over from Electron and put them directly on Neutron, and all of the software code base that goes with that. We have a giant head start in reusability from all the learnings we've had by re-entering electrons. So I think we're in a good place, having executed and done this before to meet that. But we're certainly pushing hard. That is for sure.
Okay, and to be clear, the Venus mission is going to be flown by the Electron. It's not waiting for the Neutron.
Correct.
Okay, and so using the photon, you're sending how much mass on Venus injection?
Yeah, the probe's about 40 kgs, so we can get about 40 kgs, into Venus's atmosphere.
So you'd probably be able to do almost that much into Mars's atmosphere.
Yes, yep.
Okay, so,
which doesn't sound a lot, but actually, the Nephelometer that we're flying, I think it weighs 900 grams. So, the majority of the mass is actually in the heat shield and in the radio. So, but mainly in structures, to be honest with you. So, you can do something pretty significant. And if you're not actually entering something in the atmosphere, then and you just want to orbit the photon, then you've got 40 kg payload, which you can do a lot with 40 kgs of actual payload mass. Yeah.
All right. So you could do a robotic Mars mission with an Electron launch. You're saying those are like $7 million each or something, or whatever?
Yeah. So, I mean, like I say, we did the mission to the moon for $10 million. Now, in full disclosure, I don't think we'll do that again, but you can see the order of magnitude. It's we've taken missions that would be hundreds of millions and turned them into tens of millions.
Yeah, no, that's very interesting indeed. I think I'd like to open it up to questions from people here. You don't mind?
Sure.
So I'll just call on people. And then if someone can move around with a mic, let's take this gentleman over here with the blue shirt. I want you to get him. Oh, I see.
Thank you. What lessons in manufacturability are you carrying forward from electron to neutron second stage to ensure that it has a high production rate and can guarantee a high flight rate? Are there any fixed set of lessons that you really think are going to be embodied in neutron second stage?
Oh my God. I reckon you could write a book on that, and the lessons are hard. I think, look, I used to think that getting your first rocket to orbit was the hard part. That is so much simpler than doing it over and over again. Like it's I would say it's somewhere between a 10 and 100 time factor of complexity going from your first rocket to rocket number 20. And the answer to the question is absolutely yes. There's one, as I mentioned before, there's one rocket rolling off the production line every 20 days. Right now with Electron, and the approach we took with the upper stage is ironically in the space industry. It's not very common, but in the aviation industry, it's common. It's common as mud, which is automated fiber placement. So basically, call it a 5-axis robot with a composite placement head on it. So what that enables you to do is put down, literally meters a minute of carbon down onto the mold, and you can cure and co-cure a tank in a ridiculously short amount of time. And composites get a bit of a hard rub because the cost per kg is expensive, and that is true. But actually, if you analyse the cost of building a rocket, the raw materials account for a very small amount of it. It's kind of the labour and the overhead actually account for the majority of it. So automating that makes a huge difference. And then the way that the upper stage is designed is kind of we were faced with this quandary, right? Where you need the highest performance in that stage, but it also has to be the lowest cost, and generally those two things don't go together. So the way that the upper stage actually works in Neutron is it's hung from the payload plate. So all of the upper stage below the payload plate is hung and is in tension. So normally you sandwich your upper stage and it's in compression. You've got to deal with all these bending loads and whatnot. Whereas by putting it inside the first stage, taking the load path directly from the payload out to the structural walls of the first stage, and just hanging that second stage, it basically means is that the second stage is extremely light. Like the structures are extremely light. So think of like a Centaur, which is extremely light, in very thin stainless steel, and then you swap out the stainless steel for carbon, which is a quarter of the mass, and a high specific strength. So you end up with an upper stage that is just from mass to a performance of propellant to mass ratio just really, really exceptional.
Okay. Next question. Someone.
Question over here, I believe.
Hi, how important is young talent, access to young talent with like specific skills and experience when you're doing things like full reusability or partial or reusability and complicated liquid engine maneuvers, things like that?
Yeah, well, I mean, I think that's not just specific to those particular applications. Like access to talent, I think everyone will tell you that that is a huge challenge, and what a time to be alive to be an aerospace and space engineer. Like this is the best time, and keeping the machine fed of really, really good talent is probably the thing I toss and turn at night the most about. Make no mistake, the bar to get in at Rocket Lab is extraordinarily high, and we're very, very, very fussy. But you can kind of bury your head in the sand and complain, or you can do something about it. So, we invested really heavily into education programs. We've been around 100 and it's nearly probably 200 schools now. We have apprenticeship programs, scholarships, PhDs, and we found that actually the most effective way to bring young people into the industry was not go to high schools, because by the time they've gone to high schools, kind of two things have happened. Either their dreams have been crushed or their dreams have been set. And you go to primary schools, and that's where you can actually have the biggest impact from young kids deciding to pursue a career in STEM or engineering or anything, any of the sciences. So we spend a lot of time in primary schools, and it's a long-term bet. But after 5 or 6 years of doing that, we're starting to see the benefits.
Okay, next question. Let's have this fellow over here.
Hi, Stilly Forward Moondow. So would you ever consider selling a neutron rocket? Say Carl Icahn buys a space station and wants to have a dedicated rocket for private flights up there. Is that something you guys would consider? And have you guys entertained any discussions about dedicated rockets for specific projects?
Yeah. I mean, look, we're totally in the business of selling rockets. We certainly wouldn't, fist one over to somebody and say, "Here you go." We'd happy to do a service, and we definitely, customers come to us directly to do their missions, so there is no middleman between us and the customer. So this is the way we kind of operate. As a customer will come to us with a particular mission, and we will deliver that mission for them in that sense. But I mean, as far as kind of non-space companies and kind of missions, we've done that before as well. I mean, we've launched non-traditional space companies and got their payloads to orbit as well historically.
Hello, I have a related question. So who should we contact if we have a mission proposal?
Well, if it's anything to do with Venus, contact me. But if it's to do with any other planet than Venus, the best person to contact is Richard French at Rocket Lab. So it'll be r.french at rocketlabusa.com. So Richard is leads up a lot of those mission formulations, and he'll be super excited.
Okay.
Any other
Other
questions?
questions? We have one over here.
I was wondering what made you choose to open for the second stage? What made you choose that? Because using more moving parts could result in greater chance of like a failure.
I presume this is with respect to the opening fairings. Is that correct?
Yes.
Yeah. Look, like a rocket is a giant engineering trade, just as a spacecraft is a giant engineering trade, and you're trading off the kind of the cost and complexity of recovering fairings versus just keeping them on. And the reality is that when we actually open those fairings, we're through the soup. We're at an altitude where aerodynamics and heating is no longer a force that matters. Ironically, the most challenging force we have on the fairings when they're open is the speed in which we need to open them and close them, and do the rotational burn back maneuver to get the vehicle clear of the second stage and heading in the right direction for reusability. So the highest load case on those fairings is actually opening, closing, and the boost back, not actually the ascent. But I take your point. The more parts you've got moving, then the more possibility of failure. But in this particular case, the gains that are realised from that particular actuation are just too immense to not solve that problem.
Okay, over there.
There was an early concept from SpaceX called Dragon Lab, which was the idea of an unmanned, long-duration crew capsule with no crew on board for pressurized experiments and anything. Is there any thought on when, especially during the early testing, when you're not going to actually physically send people up there to do any kind of long-duration lab work with your crew capsule?
Yeah, that's cool. Yeah, no, I like that. Well, there wasn't. Maybe there is now. But I would say that we kind of do that a little bit with Electron. So Electron's upper stage, or its kick stage, it can be turned into a satellite itself. So we have had missions in the past where we've launched a customer's satellite to orbit, and then once the customer satellite is in orbit, we literally turn on our kick stage and it transitions into a satellite. And we've used that internally for actually developing our own technology, getting time on new kind of spacecraft and satellite developments. The photon, that lunar photon that we went to the moon with, it's a blurry line between what is a rocket and what is a spacecraft at that point, because it also forms part of the upper stage. So that would be a fairly small scale, of course, but way of kind of doing a very low cost lab for sure.
Over there.
Hi. Back when you ate your hat for the announcement of Neutron, I was wondering, you said that Archimedes was designed to be sort of intentionally simple.
Yep.
Has your philosophy around that changed at all since then?
Absolutely not. So, we have had a cycle change from a gas generator cycle to a staged combustion, Oxford staged combustion. So that may kind of sound like another hat-eating moment, but the only reason we changed that architecture is because we found that the requirements of the upper stage engine were such that it requires very deep throttling. And by the time, GGs are great cycles, but methane makes it even more challenging for kind of that cycle and deep throttling for both throttling down for light upper stage payloads doing interplanetary work, and also the landing engine. So we actually found that we ended up in a position where the turbine temperature of the GG cycle was just pushing right up against a limit, and was no longer kind of true to the philosophy. So as we tried to solve that problem, we looked at different cycles, and the staged combustion cycle is a great cycle. It's generally not synonymous with low stress and low pressures and those kinds of things. But actually, what we did is we took a very good cycle and derated it. So typically, if you're running those closed combustion cycles, you have very high chamber pressures and very high pump pressures, very high temperatures, very hot oxygen. Well, we said, what happens if we just hold the ISP value the same? By the way, it's not that high, because it doesn't need to be high, and move over to that cycle. And what that results in is actually incredibly cold turbine temperatures, incredibly cold oxygen temperatures, and of course low chamber pressures, which is kind of all related, and an incredibly reliable engine. So it's all about how do we make the most boring the most reliable engine, and although the cycle is, like I say, synonymous with the opposite of that, actually when you run it, it's literally like running one of those cycles in an idle mode for where we're at. So strains and longevities, temperatures, all of those things just plummet into the right zone.
Can you describe in a bit more detail the process that you mentioned of using helicopters to catch the reusable rockets? And also, do you see this being your long-term solution for reusability?
So absolutely. So for Electron, it's a small launch vehicle, and I think, as I mentioned before, there's zero margins in a small launch vehicle. It's an incredibly difficult vehicle to fly. And if you were to do a propulsive landing in a small launch vehicle, you would get no payload to orbit. So basically, you have to let the atmosphere do the work. So for Electron, the really challenging bit for that is actually targeting and guiding and controlling the entry dynamic of that stage. So we control the entry of that stage very closely, and basically we bring it in engines first, because obviously there's a bit of a heat shield there anyway to deal with plume interactions and flow interactions you get from ascent. And if you can hold that angle of attack just so, then obviously you have a big bow wave out the front and it pushes everything out the front, and the stagnation point is well forward, and if you can get that forward enough, then you can basically sit in the lee of the flow. And with a carbon composite launch vehicle, the tolerance for really high temperatures is obviously not very high. So you have a very tight corridor to guide through. But if you can pull it off, then you don't need any burns, any control burns or landing burns. You don't need to use any propellant, and you basically let the atmosphere do all the work. And of course, if you're not landing it, then you need to be able to get it somehow. So putting it under a chute is the obvious solution. Splashing it down in the ocean works, but then you've just got a whole lot of effort in front of you to clear out all of the salt water and all of that stuff. So the logical decision was like, well, let's not let it touch the sea. I love helicopters, and it's the ideal machine for doing it. And there is a heritage of that particular mission. So we started testing it, and we found that we could do it actually really, really well. So that was kind of an example of a vehicle that was never designed to be reusable, made reusable. Now Neutron is a totally different kettle of fish. Neutron was designed to be reusable from day one. Hence you see the difference in design, the difference in aerodynamic surfaces, and the difference in even architecture. So, Neutron does use propulsive landing. It's a vehicle of a scale that will work through, but it does not have a deceleration burn. We're able to negate the need for that deceleration burn purely through, the re-entry dynamics of having a very large ballistic coefficient and very low mass.
I've got a question. Have you looked at Neutron for surface-to-surface travel on Earth?
We have actually, and we have a contract with the US government to look just explicitly at that. Obviously, there needs to be a very strong justified reason to do that transport, because I think it's a fairly expensive and it's certainly a lot riskier than flying in a plane. So
yeah, New Zealand's pretty far away from here.
Man, if I could get from New Zealand to the US, from launch site to launch site in a ballistic arc, that would be awesome. I would love that so much.
All right. Well, you need to do it. Okay. More questions here. Let's get one from over there.
Thank you. Has there been any work on human rating your vehicles at all?
Yeah, so we're designing Neutron to be human rateable. It's not coming out of the chute as human rated for a couple of reasons. One, look, you just got to fly a whole bunch of cargo first. And I have just such incredible admiration for an astronaut. I don't think I could ever climb aboard a launch vehicle. I know the failure modes too well. And at the end of the day, it is an incredibly complex machine, and you do everything you can, but you have to accept there's significant risk there no matter what you do, and you can mitigate it pretty successfully for sure. But before we want to fly any humans, I'd like to see a lot of kind of less precious cargo first, and really get the vehicle well buttoned in. So for logically, we're making it human rateable, and what that means is like we don't want to go back and requalify all of our tanks and go back and have to change tank wall thicknesses because safety factors aren't where they need to be. So we're making sure that all of that is built in from day one. But the actual certification process is a massive process. So that's what I mean by making it certifiable, but not certifying it from day one.
About right here.
Yeah, I'm a scientist who's interested, of course, in the life on Venus question. And of course, we're motivated by Jan Spacek has this carbon cycle on Venus, which leads to glycolic acid and maybe explains the pale yellow, lemon yellow color that Venus has. I mean, don't worry, your team is working with Jan and it's informing the nephelometer. So But I'm concerned, interested about your motivation. So is the science fundamentally motivating such that if somebody told you that life definitely does not possibly, could not imaginably exist on Venus, and you believe them, which would be a separate point, would that make you less interested in Venus?
Oh man, that's a deep question. Well, I guess it would have to. I think I wouldn't be true to myself if I said it would have to. I mean, I have, for whatever reason, I just think that's a really, really important question to answer. So if someone else, if it was answered either way, I'd be extraordinarily happy. Now, if I can be a part of that answer, it's neither here nor there. I think Venus is an interesting planet other than just the fact of life. I think it's an incredibly interesting analog, and from an atmospheric standpoint, it's just like the more you learn about Venus, it's just like the definition of like an alien world. It's just super nasty. So no, I definitely think there's a lot to learn more about Venus. And I still think we need irrespective of picking favourite planets. I think we need to do much more research in our solar system and in our planetary bodies either way. I think there's a tremendous amount that we need to learn. So yeah, I mean, I wouldn't cash in my chips if that's what you mean. I'd still be pretty keen.
Over there.
We all talk about a STEM education, which is both appropriate and good, and I don't think anyone disagrees with that. But in a more practical way, you need people that can do things now.
Yeah.
The evolving industry means that job descriptions and definitions are being firmed up. They're starting to be shared across the industry. So if you were to state what kind of skills you needed in the next couple of years, I mean, 1 or 2 years, what kind of descriptions would you be seeking?
Yeah, that's a really great question. Look, I guess for me, what comes first is people's passion and motivation. I think that always comes first. We'll look for somebody who's just gone out and done something versus somebody who's done nothing with a flawless grade. So I don't think it's just about education. Obviously, you need a baseline of education, to be able to be, knowledgeable. No, even then. I mean, I never went to university, and there's different ways of obtaining knowledge for sure. But I mean, I think the priority for us when we're looking at candidates is motivation and passion and actually just doing stuff is number one. But I guess you can pick your field, honestly. Like, if you said there's no one particular field that we're like massively flush on, like all of the fields from across our space systems division and our launch division, whether it's aerodynamicists to structural analysis to technicians on the shop floor, it's all across across the board. And one of the things that we actually find a stereotype, if you will, is especially in the kind of the technician environment, is actually convincing people that you can work in this, and convincing a technician that in fact with the right level of training and support that they can work in the space industry and work on really important complex things. So I think some of the workforce may believe that they're not capable when in fact they turn out to be amazing. So I know that's not a really great answer to the question, but it's a very difficult one to answer.
And are you hiring?
Yes, we are hiring. Yep, rocketlabcareers.com, please. Yep.
rocketlabcareers.com, kids. There it is. All right, right here. Okay.
So great for you to speaking here. Thank you. And we could ask you a million technical questions. I'm interested in you, the person, the leader. You talked about education. You talked about motivation. But you've had sustained creativity and sustained risk taking and extraordinary outcomes and success. how do you manage failure as a leader, an individual, and as a company and cultural? Do you have something cultural that's unique at Rocket Lab that you would like to share with us, or perhaps not share with us?
Well, firstly, your comments are very kind, but you know, like the cake always looks great when it's presented on a plate, but man, the kitchen's messy. You know, there's a heap of really challenging things and failures along the way. I mean, I think the culture in the company is like the bar is high, as I mentioned, for talent. The culture we have here is that we have everybody's back, and I guess the thing I'm most proud of about the company, and a company is not a logo. It's not the CEO. It's a collection of amazing people. And the thing I'm most proud about, the company, I think one of the things that's special to us is that when there's a problem and when something goes bad, nobody looks at each other and goes, oh, it was their fault or it's their fault, or nobody ducks for cover and looks to hide. Everybody acknowledges that, okay, that didn't go the way we were expecting it to go. And everybody just jumps in and tries to solve those problems. And, if there's a failure in avionics, you'll find the software team will be the first team there to help out, or vice versa amongst the company. And I think that's part of the magic of the company is that we're all passionate people. We all want to see success, and we don't want to see anybody else fail within the company. And that's pretty special.
Okay. Musk has adopted the approach recently of basically mass producing his vehicles before they're even been proven to fly. So his strategy is produce a whole bunch of them, launch them, crash them, fix what that failure was, launch the next one, crash it, fix the and so forth. Now he can do that because he's got deep pockets, but it also has proven to be a pretty muscular approach to development. Do you have anything like that in mind, or what's your approach going to be?
Yeah, my approach is slightly different there. And not to say any approach is better than the other, but we have a fail fast mentality at Rocket Lab. But look, it's at the component level and at the subsystem level. By the time we get to full up assemblies, we expect them to work, and maybe that philosophy and that approach has been born out of the fact, as you say, it's like if you don't have infinite capital, then you don't have infinite possibilities to, you have a finite amount of tries. So those tries, better be well reasoned. But, I've found that, at least in my experience, that there's a right place to fail fast, and like I say, we'll fail fast on early concepts and things like that, and even early sub-assemblies. But we like to put a lot of because you can go too far, right? You can sit and do endless analysis. It's very easy to sit and do endless analysis and continue to come up with questions to answer, and at some point you just have to, say, let's just go and build it and see what we've actually got. And I would say that, if you had to draw kind of a line of where we're at, we're probably in the middle of between way too much analysis and no analysis, and study, I should say. So, our approach is different. Whether or not it's better, who knows? But it's the approach that's kind of worked for us. And like I say, when we get to really expensive big things, we really don't like seeing those fail.
Okay. So finally, because we're almost out of time, when Neutron flies the first time, where is it going to fly from, and will people be able to go there and see it succeed?
Yeah, look, it'll fly from the Wallops test facility, so that's where we're building the pad, and of course that's a great launch site to view. I will caution it's a first flight, so all of the risk that's associated with a first flight.
All right. Well, good luck. Thank you very much. And once again, it's rocketlabcareers.com. Thanks.
Thanks, Robert. That's awesome.
Yes. Okay, folks, we're going to go ahead and reset. Now, I have a couple quick housekeeping announcements. By the way, my name is James Burke. I'm our lead conference organizer. I hope you guys are all having a good conference. We are a conference that's 100% organized by volunteers. So if you see a volunteer, thank them. You can tell they're the ones in the back with the microphones. We have a couple of really exciting things happening for the conference. We have a live music event tomorrow night in downtown Phoenix at Last Exit Live called Mars Rocks. We also have a reception tomorrow night at the ISTB4 building, which is a short walk from here. If you haven't been over to that building, I highly recommend you come to the reception tomorrow night at 6. That building is like a mini JPL. They have a full-size Perseverance rover in the lobby, full-size Psyche spacecraft hanging in the lobby. So it'll be well worth your time. And then we'll have buses to take you to the live music event for those of you that are 21 or over. By the way, is Colleen in here? So Colleen is one of our sponsors with Whistle Pig Whiskey. And tonight at 9 o'clock, so right after our public panel, for those of you that are staying at the Hyatt, there's a rooftop bar, and we're going to have some free samples. So join me there if you're at the Hyatt, and if not, we'll come to the live music event tomorrow because she'll be there as well. One last housekeeping announcement. We have a merch table this year. It's 100% organized by the Mars Society. My daughter Cleo is actually running it. She's in the back right now. And so swing by. It's in the La Paz room, just right around the corner from here. Let's see what else.
One quick thing.
Yes, go ahead.
Yes, I did buy gear. I highly recommend it. It's totally worth it. For tonight, just 21 and over. Cool. Okay, that was it.
My apologies. We are on a college campus after all. And by the way, we tried really hard to get a liquor license for the reception tomorrow night at ISTB4, but that didn't happen for a lot of reasons. So I'm gonna go ahead and reset the Zoom here. I'm next. We're gonna talk about my project Mars VR. And so just give me one moment. Robert, do you have?
Yeah. One thing is, there's a lot of volunteers that are helping to run this conference, and we just want to really thank you for what you're doing, because this doesn't all happen by itself. So let's have a round of applause for the volunteers.
Thank you. All right, so for those of you that are online watching Peter Beck, we are now going to switch over to the special presentations webinar. For the next 2 hours, that'll be the webinar for this room. There's also some other talks happening in the other tracks. So we'll see you on the flip side on the online folks.